I am reviewing for you today Lab 3, determination of the empirical formula of silver oxide. So we're dealing with this compound silver oxide, which is the oxidized form of silver. It's one of the tarnishes. And so we have silver bonded with some oxygen. And I know that because I hear the word silver, which is the name of the element in front, and the oxide, that oxide ending, the IUPAC way that we name salts, we know we're dealing with an element or just one element beyond silver. If it had a name of a polyatomic ion like carbonate, we would have a group of them with a charge. So I know it's a binary compound. The idea that we're looking for the empirical lowest ratio is understood because we are essentially dealing with a salt. A salt, of course, is a metal or positive ions attracting negative ions in some form of crystal lattice. Okay, I'm drawing a very simple one, but essentially what you understand is all of these types of compounds, if they're in their solid phase, are in these crystalline structures. Of course, the negative ion would be the oxygen. So what we've got to do is we've got to apply heat to pull these negative ions that are electrostatically attracted to the positives, these silvers, which tend to be pretty small, to pull them out of those positions. Okay, and then of course it's a redox reaction to make elemental oxygen, and of course the silver, okay, would of course become the silver zero, okay, or elemental silver. So we're going to have a redox reaction going on, and it's not important that you totally get that, but you should understand that we're dealing with silver plus in the crystal, and it's becoming silver zero, and that's a pretty good important background understanding, and I'll write that again. So we've got silver plus 1 in the crystal, and it's becoming elemental silver in this decomposition reaction. Well, why? Well, it's because it's taking in an electron. It's getting reduced, as if you remember that. And of course, the oxygen, okay, is -2, and it must be what? Losing 2 oxygens, okay, two electrons to become oxygen 0. Now, because oxygen loves to become diatomic, okay, so therefore this is going to throw a 2 here, a 2 here, and this of course will make itself a 4. Okay, and if I am losing 4 electrons, then somehow I'm gaining 4 electrons, and we'd balance that out. But I'm not really after the redox here, just being aware that we're creating what? The elemental form of these atoms that are in an ion form. And the reaction that you're dealing with is essentially silver with oxygen. We don't know the chemical formula. That's what this lab is about. And we're heating it, okay, to force the ions away from each other, to give them a chance to have that oxidation reduction reaction to occur, to make elemental silver, which will be a powder form, and the oxygen gas, which is going to leave. And now we know that to be diatomic. The question is, what is this formula? So if we think back to the days of the 1860s, where most of this occurred after the major conference where Cannizzaro gave the world Amadeo Avogadro's work so they can figure out, using the mole concept, how to understand how to use the ratio of atoms with each other to build chemical formulas. This was done during that time period. So in any case, that's essentially what we're doing here. Now, what else is going on is that when we're dealing with silver oxide, what we're trying to do in this lab is figure out the mass of the silver and the oxygen. Very understandable. We want the mass essentially of the silver, and we want the mass of the oxygen. So very simply, what we're doing is we're finding the mass of the silver oxide, all right? And then we're heating until that mass gets lowered, because we're going to drive off all the oxygen. And we're going to keep heating and remassing. So we mass our silver oxide, then we heat, and then we mass what's left over in the crucible. Now the crucible, of course, is that porcelain piece of equipment that is used to heat things. And over time, we're going to drive off all the oxygen. Now we don't know when that occurs, so we keep heating and then massing. Now the numbers are going to drop. Obviously, as silver oxide is released, okay, then your value keeps dropping. But as you approach a point where you've driven off all the oxygen, the silver okay, mass stays relatively constant. So we keep heating and massing until the mass goes down until some kind of constant value. Now that constant value is usually to the hundreds place, since we're using a scale out to the thousands place. So we get to a relative constant. And that's how we check to see. And that's a very basic a way of knowing experimentally when we have driven off all the water or all the other compounds. So we subtract out the crucible, and what we're going to get is the mass of our silver. Knowing the mass of our silver, we subtract away that mass from the original silver oxide mass to get the mass of the oxygen. So if you didn't follow that, I'm going to have the mass of the silver, okay, that's remaining after I've heated several times to check, okay? And then I'm going to subtract out the crucible's weight. We should know that. So when we started our lab procedure, the first thing we did was take our crucible and its cover, and we heated it gently. Why'd we heat it gently? We heated it gently so that we can drive off all the impurities or any water. We let it cool to room temperature. It's important that you do so. And we put it on the scale. Then we heated it again, and then we heated it gently to drive off any water impurities inside the crucible, and then we massed it out again on the scale. If the masses were constant and not changing, we know we have an empty dry crucible. And then that mass is the mass of my crucible, which you'll see on the bottom, top of the lab, the mass of the empty dry crucible. Okay, then we add some silver oxide to the crucible, and of course it gets heavier. All right, at this point you could subtract out these two values, and that's give you the mass of the silver oxide, which is right here. Now number 3, the mass of the crucible cover and the silver product. That's after you've driven off all of the oxygen. And now I didn't put it here, but you should have places in your table or your lab book where you're showing heating and remassing until what? Your crucible gets light enough, where it doesn't change anymore. Okay, and then at that point, you find the mass of your silver by subtracting out the dry crucible and cover. If you have the mass of the silver product, you can get the mass of the oxygen by subtracting that mass of the silver product, okay, from the what? From the mass of the silver oxide. And now you're off and running. Once you have your mass of your silver and your oxygen, we know from our mole concept that we have to convert these numbers, okay, into what? We have to convert these numbers into a how many number. So we convert to moles here. And then we divide by the smallest moles. And that would give us, okay, the moles of the oxygen, the moles of the silver, and then we have our ratio. Make sure when you write that ratio, if you get, 1.8 to 1, write it. I want to know that value. I know you might be rounding that to 2 to 1, okay, or what have you, but I want to know the actual number because I want to discuss why it's not exactly 2. Now we know if we were to do this lab hundreds and hundreds of times and you got better at the technique, okay, probably this number fastly approaches 2, okay? But doing it once or twice, you don't have the technique down or the confidence in yourself to get really accurate data. It takes time, and we just don't have time to do it that many times. But that's what they were doing in the 1860s, is they were doing these over and over and over again just to make sure that we got whole numbers. And of course, these whole numbers were verifications of whole number differences in atoms, okay? And of course, we built our empirical formula based on these ratios. Now, if you understand that, you need to understand some background in this lab. Okay, because there is some going to be some error here. You're not going to come out perfectly 2 to 1. You should all be aware that silver oxide, no matter what the formula is, and I'm just writing it AgO for now, okay, is a very important scrubber of CO2. It can absorb CO2, okay, and what it produces is a silver carbonate. And so one of the problems we may have in a lab is that when you were to mass the original silver oxide, you might be measuring out silver oxide and silver carbonate. So that may be something you need to talk about definitely in your discussion regarding why your value wasn't a perfect 2 to 1. Okay, I do not want to hear that, well, we need to do this 200 times to get our techniques down. I want to know why there was some error here. Okay, so one of the things is that. Now, honestly, when they use this to scrub, okay, the CO2, that means the silver oxide, and by the way, they do this in nuclear submarines mostly. Silver oxide takes the CO2 out of the air to make silver carbonate. What they can do is take the silver carbonate and they can heat it, and it's about around 210 degrees Celsius. If you heat it beyond that, you can reclaim your silver oxide. Again, I'm writing AgO as my empirical formula. It may or may not be right, wink, wink, okay, plus the CO2, and you can restart this. However, what we did in our lab to get rid of the oxygen in the silver, we heated it beyond 210 degrees Celsius, around something greater than 280. We drove off the elemental silver and of course the oxygen. So just be aware of these reactions occurring, because if you remember, one of your techniques of using a crucible is to cool your crucible and then mass. And if you're cooling a crucible, there may be CO2 that might be what? Involved with the silver oxide that you're heating, and maybe forming silver carbonate. Something else to think about in terms of your errors. Now, in your errors, don't just tell me, well, silver carbonate was being reformed. Tell me how it led to your value, in this case that I'm giving you, that's below 2. You just can't tell me the errors. You show me and talk about the exact math that did that. Now, write a balanced chemical formula. This should be on the empirical formula that you found. I know that you're probably rounding to whole numbers, and that's okay. All right, the theoretical yield of elemental silver. Knowing your balanced formula, okay, and let's just pretend that this is sort of it, okay, and using the correct stoichiometric coefficients when you balance, tell me exactly how much silver we're supposed to make based upon how much silver oxide we have. Of course, we're assuming what? It was pure silver oxide, which is tough because it loves what? CO2. Percent yield is what you actually got. Okay, what you actually got was the mass of the silver after heating it and verifying that by remassing it, reheating it, remassing it. So the mass of the silver product, that's your 5. That's what you got experimentally. And then theoretically, you just did that in 14. Okay, and that's how you find your denominator, and that's how you find your value. And of course, there's your error analysis, which I've been talking right along. I do not want to see human error. Do not even mention it. I don't want to hear the idea that we need to get better in this technique. That's true, but I want you to try. Let's assume that you are perfect in your technique. Okay? I don't want to see measurement error. Well, it'll be hard to measure. We measured wrong. That's not a great discussion. I want to think about what could have happened in the lab with this crucible that may have, you don't know for sure, but give me a what? Give me very, very good sound logic of why you're under, and carry the math through. The one way to think about this college level error analysis is carry the math through to see how it would lower the value. Okay, hope that helped.